Welcome everyone around the world to this next section of the Science at Low Frequencies conference. This is called session 8, entitled Milky Way Galaxies and Clusters. We have 6 presentations. The first one 30 minutes and the rest 20, if I look at my schedule correctly. And so let's start off with Beatriz Mingo at Open University. She's going to speak on AGN accretion mode versus radiomorphology, news from the LOFAR Deep Fields. Take it away.
Should be able to see my
presentation
slides. All right, here we go. Thank you, Rick. So thanks everyone. Thanks to everybody that's here and is awake at the moment or somewhat awake. And thanks to the organizers for giving me a chance to present these results. So as Rick said, I'm going to talk about some recent results we got on the LOFAR Deep Fields in terms of comparing radiomorphology and accretion mode for a sample of result of large radio galaxies. And as you can see, this is work that has involved a long list of people to whom I'm also very, very grateful. It's work that we recently submitted to MNRAS for publication, and I'm dealing with a referee report right now, so hopefully it will be published soon. So when we talk about radiomorphology, we are essentially talking about the interaction of the jet with the environment, and this is something that has been a subject of study since the mid-1970s. The famous paper by Farnaroff and Riley, which divided sources into a Farnaroff-Riley type 1s and type 2s, depending on whether they were center brightened or edge brightened. So center brightened sources are called the FAR1s. They're center brightened because the jet interacts with a dense environment closer to the black hole, and the jet gets disrupted earlier. While FR2s, essentially the jet remains collimated for a large distance and eventually slams into something and creates these bright hotspots. So they are edge brightened. And we know that traditionally FR1s have been associated with lower power sources and denser environments, and that's why the jet gets disrupted quickly. While in all the surveys, FR2s are more powerful and they live in sparser environments. We know now that in recent surveys, we have started finding low power FR2s, and I'll discuss this in a little more detail soon. So there's also obviously the cases in between the two extremes, which is where the interesting things happen. It's the reason essentially why we still care about morphology 50 odd years on from this original classification, why we still try to bother putting labels on these things, because, you know, at the end of the day, we care about the physics that are happening in these environments. The morphology is telling us something about the underlying physics, the underlying properties, where the energy is getting transferred. And we know that FR1s and FR2s have different particle contents, they have different hosts, they live in different environments, and they have different magnetic field properties as well. Something else we need to keep in mind is that the way we classify things is hugely dependent on the surveys, on the instruments that we're using to see these things. So things look different at different frequencies, they look different at different resolutions and at different depths. So I encourage you all to think about classifications as not a closed box, essentially, where you put sources and never take them out, but actually apply labels that are related to the survey, to the instrument that you're using, and keep in mind that these classifications are not absolute. And also, again, keep in mind that in terms of frequency, going to lower frequencies is very advantageous, because you can start seeing older electron populations, you can start seeing under emission and more extended emission than you do at higher frequencies. So you obviously need both to try and understand the evolution of these sources. I don't need to sell low frequencies to you. You won't care about this. The other reason why we care about the morphological properties, the shape of these sources and what they're doing, is because they allow us to build a better picture, a better understanding of how radio galaxies, how radio sources evolve and how these populations fit together. So you see here, you're probably all familiar with this diagram, which has the luminosity at 1.4 gigahertz versus the size, essentially, and different types of radio sources. You have the compact ones here, FR1s and FR2 here, radio quiet quasars here, and here the very low luminosity liners and CFERTs. So understanding how these populations fit together, what conditions give rise to each of the classes, which ones evolve into each other, what are their life cycles, and therefore what their impact is on their hosts and their large-scale environments is very, very important, because this is what allows us to understand the evolution of galaxies and the universe in general. So back in 2019, we wrote a classification code called LOMORPH, which you can find in this GitHub repository here. You can see more about, you can find out more about lots DR1, the upcoming DR2, by the way, in Teaching One's talk tomorrow. As I said, as I was saying, we wrote this classification code that essentially puts sources into FR1 or FR2 classes based purely on whether they were brighter in the center, so on FR1, or brighter at the edges on FR2. And we threw this at the entire LOTS DR1 survey. And you can see a summary of the results here. This is the 150 megahertz luminosity versus size on the x-axis. You can also see these triangles indicating the parts of the parameter space that we cannot see with the data. And the traditional boundary dividing FR1s and FR2s in terms of power. You can see some of the results are expected, some of them are unexpected. If we had carried out this same exercise with an older survey, say something like FIRST and VSS, we would have found that overwhelmingly the FR1s would be below this dashed line, and the FR2s would be, almost all of them would be above this line. And you can see that the FR1s mostly behave as expected in these results, but the FR2s really don't. Roughly 50% of the FR2s in our LOTS DR1 sample fall below this traditional boundary between the two classes. And even if we go about an order of magnitude below the line, we can still find about 20% of the sources below this luminosity. We had a look at the spectral index distribution of this population, where we had good data to constrain it. And we figured, also in terms of sheer numbers, these low luminosity FR2s cannot be explained just as fading counterparts to the very bright ones above the line. What we did find, interestingly, is that their hosts seem to have lower stellar masses than those of the equivalent FR1s. We could only do this with KS magnitude distributions, which obviously is an indirect way to measure this, but it's still the difference was significant. These sources seem to live in lower mass hosts than the FR1s. And this makes a lot of sense. If you have a low power jet, but you don't really have anything to disrupt it, to stop it, you can still produce an FR2. It doesn't need to be very powerful if you don't really stop it with anything. But the key consequence of these results is that you can no longer make assumptions. We can no longer make assumptions on jet power based on morphology alone. If we see an FR1, we know that it's going to be a fairly low power source. That hasn't changed. But if we see an FR2, we cannot tell purely on its appearance whether it's a low power source or a high power source. All that we can say is that it's edge bright and that it has a jet that doesn't stop at the host. So linking this to accretion mode, accretion we care about because it's telling us something about the physics where the jet is produced close to the black hole. And it's also got to do both with what we observe in all the wavelengths in terms of what the AGN is doing and on the influence this AGN is having on its host galaxy. It's also telling us something about the cycles of these sources. This is a diagram that people refer to fairly often. It's the activity or duty cycle of an X-ray binary, a low mass X-ray binary at that, so the equivalent to an AGN, a small black hole. And at the end of the day, it's accretion onto a compact object, so some of the physics are fairly similar. X-ray binaries go through these cycles. We can start, for example, at this low hard state. Spectral hardness here refers purely to X-rays. So in this end here, we have a very slow accretion source, a radiatively inefficient source that's not producing a lot of luminosity and has low power steady jets. And as the accretion rate goes up, it follows, the source follows this blue line on the diagram, this blue arrow. The jets start getting more powerful, they get relativistic, and we transition into a radiatively efficient regime where we produce a lot of luminosity. And eventually the jets are switched off and the source moves into this soft state where it goes back and forth for a while. This is a radiatively efficient state where there are no jets, and eventually it transitions back to this low hard state, the LERG equivalent, essentially. We know that X-ray binaries in AGN, as I was saying, have some similarities, but they are also very different in various respects. X-ray binaries obviously have black hole masses equivalent to that of our sun, or a bit larger, while supermassive black holes in AGN are many orders of magnitude bigger. And the timescales involved in these cycles are also very different for X-ray binaries. You can observe these cycles, the whole transition, in terms of days to weeks to months. And in AGN, this takes millions of years. But two of the key points in which these sources are different are the fueling and the role of the black hole, specifically the black hole mass. So X-ray binaries always have a supply of fuel available to them. They have a companion star that is always providing gas, and they self-regulate. It's the black hole regulating the accretion and regulating the cycle. In AGN, obviously, you depend on an external supply of gas that can have different properties, different angles. It might be there, it might not be there. So in this sense, it's very different, and they might not necessarily follow the full cycle here. They might behave very differently. But also the black hole mass is very important in terms of where you are in this diagram, because transitioning from an inefficient, radiatively inefficient to an efficient state it's m dot. So it's the amount of mass that you put onto the black hole divided by the black hole mass. So if you have a very, very massive black hole, like the ones you find in cluster center galaxies, those massive LOFAR ones, you find it very, you need a huge amount of gas to transition from a radiatively inefficient to an efficient state. While if you have a lower mass black hole, it's a lot easier to just move through this and be radiatively efficient, for example, most of the time. You just need a little gas to push you over the edge, essentially. This is not a variable that we need to consider in X-ray binaries, but it's very, very important for AGN. So where you find your AGN, essentially the likelihood of finding an AGN in the equivalent parts of this diagram for AGN depends on the host stellar mass, which is linked to the mass of the black hole. It depends on the environment, which is linked again to the type of galaxy that you're in and to the gas it might have to fuel the black hole. And it depends on what accretion rate you can produce on the mass of the black hole and how easy it is to get over this edge. And we know that in all surveys, nearly all of our ones have been found to be LERGs, so down on this end. And most of LOFAR2s, but not all, particularly not at all low luminosities, have been found to be HERGs down here. But with LOFAR, we see new populations, particularly new populations of FR2s, which look very different from the ones we have seen in all the surveys. So this is something that we need to explore to understand their life cycles and the impact they might have on the surroundings. So that's the motivation. And the ideal sample to do this with is the one we have from the LOFAR Deep Fields. The LOFAR Deep Fields are Eliason 1, Lockman Hole, and Booties. In total, they are a tiny square in the sky. Essentially, it's 25 square degrees, while LOTS-DR1 was 424. But they have a much deeper. Much deeper sampling. So the noise limit is about 20 to 40 microjansky per beam. This gives us a source density of about 5,000 sources per square degree, which is 7 times the source density that we find in LOTS. But also something that is key to try and do this sort of study is that we have incredible multi-wavelength coverage. These fields have been covered at many, many wavelengths. This allows us both to characterize the hosts in terms of their spectral energy distribution, so we can see both the accretion properties of the AGN, whether it's a HERG or a LERG, radiatively efficient or inefficient. But we can also see the host mass. We can derive the host mass in terms of stellar mass, and we can derive the star formation properties. And also we can identify many more hosts. We have hosts for over 90% of the sources in the LOFAR Deep Fields survey, which is something quite incredible. You can see the main papers here. You can also find them on the LOFAR surveys website. For the SCD distribution, the spectral distribution properties, I refer you to Best et al., which will be submitted for publication soon. And Rohit has presented some results in terms of the accretion mode of these sources. This is just a figure of merit comparing the effective RMS versus the survey area for LOTS Deep, which is down here, compared to LOTS DR1 and DR2, the shallower surveys, which are these indicated with these 2 arrows. And you can find first NVSS sums and so on up here. So we are essentially on a regime that's like 50 to 70 times deeper than first by comparison. So as we did for LOTS DR1, we threw our classification code at all the extended sources in the survey, and we found in the sample, and we found whether they were FR1s or FR2s based on where the brightest points were. And we threw them onto this luminosity versus size plot. And you can see, in this case, I've colored the low luminosity FR2s in red, just to distinguish them from the high luminosity ones in blue a bit more easily. And we also have the accretion properties here. So anything that's surrounded by a black diamond here is a HERG. It's a high accretion, fast accretion source. We found that the overall size and luminosity distribution of FR1s and FR2s and the ratios of luminous and faint FR2s are very similar to what we found in LOTS DR1. If you remember it here, you can see that the shape of the plot is essentially the same. Only obviously the sample is a lot smaller because it's a smaller sky area. In terms of accretion properties, we found that overwhelmingly the FR1s are lurgs, which is something that's entirely consistent with what we have seen in past surveys. We see that the FR2 at low luminosities are also predominantly lurgs, which again is something that we have found in the past, obviously in smaller numbers of sources. This is not surprising. These sources are a lot more similar to FR1s in terms of the jet properties and the jet power than they are to the luminous FR2s. And surprisingly, we found that 2/3 of the luminous FR2s are also lurgs. This is something that's entirely new. This is a small sample. In total, we have about 286 sources. And we cut at redshift 2.5. So in this sense, we're going a bit deeper and we're going a lot further in redshift than we did before. So finding so many lurgs among the bright FR2s was a complete surprise. By comparison, only 15% of the FR2s in the Tujansky survey and 13% of the ones in 3CR are lurgs. Those are all up in this high luminosity end. Most importantly, these lurgs are invisible beyond the radio. These are ninja AGN. If you don't look in the radio, you might confuse them for a passive galaxy, either a star-forming galaxy or a red and dead elliptical. So they're not identified as AGN at all the wavelengths. So we need to understand what's going on with them and why they look so different. This is just for comparison. These are the FR2s in 3CRR, and black circles are surrounding the Hurgs, and you can see that there's very, very few lurgs. Obviously, we're covering a much higher luminosity end in here, which you can see a bit better on the plot on the right, where you have the fraction of Hurgs and lurgs for the deep fields at the top and for 3CRR at the bottom. In both cases, the lurgs are in orange and the Hurgs are in purple. And you can see, again, we cover a slightly different luminosity range. These are only the FR2s, but it's striking how the fraction is so different in the parts of the plot where things overlap. It's obvious that there is some dependence with luminosity. As we go to higher luminosities in both samples, we have a higher proportion of Hurgs, but in the deep field sample, they seem to kind of stall. We don't have more sources at higher luminosities. So as we open up more sky area, this is something that we're going to have to see how this evolves. In the case of 3CRR, they essentially completely dominate at the very high luminosity end. But in any case, even in the medium intermediate luminosity end, the fraction is completely different. Interestingly as well, we found that there is no visual difference between FR2s at high and low luminosity or at high and low accretion rate. You really cannot tell them apart visually, and not in terms of many of their parameters. So in this slide here, I have 4 FR2s. These are drawn at random from my sample. The first 2 are low luminosity ones below the dashed line that I showed you in the luminosity versus size plot. These 2 are high luminosity ones. So these are above the line. The first and the third are slow accretors, they are lurgs. The second and the fourth are Hurgs. You really cannot tell them apart. They are indistinguishable. So the direct consequence of this is that you can produce FR2 structures at any luminosity and at any accretion rate. And you can no longer make assumptions on the accretion mode of a radio source based on morphology alone. You can for the FR1s, you know they're going to be predominantly lurgs, but you cannot do that for the FR2s. You cannot look at one of these and say, yes, this is obviously luminous and this is obviously a Hurg. Going into what produces the FR2 lows, why these sources end up as FR2s and not as FR1s when they have very low powers, the key seems to be, again, we can confirm this a bit more accurately now with our constraints from the SED fitting results. The key seems to be the host mass, the host stellar mass. So on this plot here, you can see the 150 megahertz luminosity versus the stellar mass for our entire sample of sources with, again, empty diamonds surrounding the Hurgs. And here you have a histogram distribution for a sample of matched FR1s and low luminosity FR2s, so with this luminosity and size range. And you can see that in terms of host mass, there seems to be a point of transition around 10 to the 11 solar masses. So above this point, essentially for hosts that are more massive than this, you have a higher chance of finding an FR1 than of finding an FR2 low. But below this point, you're more likely to find an FR2 low, which is interesting. Again, this is something that hasn't been observed before. And you can see that essentially spread out on this plot on the left. You can see that, yes, there are a few massive low luminosity FR2s up here on this end, but there is a big tail of low luminosity, of low mass FR2 lows spreading all the way out to fairly low stellar masses, actually. There is, interestingly, there is no difference for the high luminosity FR2 highs in terms of whether the host mass is making any difference in terms of Lurg and Herg distribution. There is a bit in the low luminosity end. In terms of whether you're more likely to find a Lurg or a Herg, the key parameter seems to be not the mass, which is surprising again, because this is something that has been found in the past to be one of the dominant things. The key parameter seems to be the star formation rate, the specific star formation rate in our case. So you can see again here the luminosity plotted against the specific star formation rate for all the FR1s and FR2s in our sample, above and below the line, with the Hergs indicated with diamonds. And you can immediately see here that almost all of the Hergs are at fairly high star formation rates. And when we plot this as a histogram, this is regardless of their FR morphology. You can see that there is a point in which you start having Hergs. There is a specific star formation rate above which you can start producing Hergs. Below that, it's very, very hard to find them. Interestingly, though, you don't stop producing Lurgs at high star formation rates. There is a tail that continues on. So there is a population of Lurgs that have high star formation as well. This is something that Rohit has covered in more detail in his paper and in his talk. So I encourage you to go and look at that. It's also obviously interesting to know that the Lurgs outnumber the Hergs by a factor of about 7 in this sampling, and there is no overall link to stellar mass, as I was saying. The tail of these high star formation Lurgs is mostly driven by FR2s, as you can see clearly here, and these seem to be mostly lower mass sources. So this is something that again needs to be analyzed in more detail. The surprising thing here is that obviously when we talk about specific star formation rate, even though it's divided by the host mass, it's still a global property of the galaxy, while accretion is linked to the central part where the black hole is. So we weren't necessarily expecting to find this correlation. Yes, it's linked to gas availability. You need gas to make stars, and you need gas to make the black hole radiatively efficient in terms of accretion. But these are on fairly different spatial scales and obviously working on different time scales. So finding these is very interesting. The next thing we will want to focus on is trying to understand the agents and the timescales of recurrence of these sources. This is something that we haven't tackled yet, and we will do in the future. So you see here a few references to papers, partially or mostly done with LOFAR, in terms of different timescales for FR2s. There's remnants, restarters, double doubles, giant radio galaxies. So we know from obviously earlier results and what we have been finding with LOFAR, we've been doing a lot of work on this in recent years, that FR2s can reach ages of between 10 and 500 million years, and they have recurrence timescales of between 1 and 100 million years as well. But these vary hugely depending on the type of source. For example, for smaller sources, things can be a bit faster and they can be shorter lived. And we can also get some deductions from things like the Wise color plot, which is this thing here that tells us something about the properties of the hosts, and where we find these restarted sources, which are the hexagons, the green and yellow hexagons, which seem to be mostly here. So the sources that we see, the way to interpret this is that sources that we see restarting on timescales that we can observe are mostly hosted by galaxies with some star formation. So they're not the FR1s. The FR1s are mostly switched always on. They're always Lurgs, and they have the jets almost on the time, as Salvatore said found in 2019. But this still doesn't tell us anything in terms of different populations of FR2s. This is something that we need to look at in detail, because we have found, as I said, that FR2 Lurgs are a lot more numerous than expected, and we know very little about these luminous FR2 Lurgs. We need to figure out whether there is an evolutionary link between FR2 Lurgs and Hergs, and between FR2 highs and FR2 lows at high and low luminosities. We need to understand the life cycles and their potential impact, because it's something we haven't observed before. And we can do this by using data from the upcoming LONS survey. This is the survey at 55 megahertz. This is just, obviously, this is not an FR2, it's a star-forming galaxy, just to show you a comparison. This is from the preliminary data release that was released earlier this year. So very briefly, I wanted to touch on some of the other work that we have been doing. Rohit's talk, if you missed it this morning, please go and look at it. This is one of the key results is that he finds different dependencies with stellar mass in Lurgs that have different types of hosts. So the lurks in quiescent and star-forming galaxies have different dependencies with stellar mass. Even when you divide things by redshift, there is an evolution that happens in star-forming sources that doesn't happen in quiescent ones, which points to a different fueling mechanism in different host galaxies. I wanted to also briefly touch on work by Brendan Webster, a PhD student who's just finishing up. On a sample of galaxy scale sources. We studied a sample of about 195 radio galaxies that are roughly the same scale as their host. This is the first sample of this kind that has been possible. This is not something that was possible before LOFAR happened. And we did a follow-up of 9 of these sources with the VLA recently. The key results here are that, even for the lowest power of these sources, and they tend to be fairly faint, at least half of them are capable of greatly influencing the evolution of their hosts, even when they don't drive shocks, and we find that a very high proportion of them do. We also found the first ever galaxy scale jet that is a remnant source, which is this one here. So even though they are not very different from your average radio galaxy in terms of spectral index, these things are key probably to the evolution of their host galaxies. So they're fairly important to follow up.
Yeah. So Beatriz, a 5-minute warning.
Yep, I'm nearly done.
Okay,
the last thing I wanted to mention today was these other brief results that have just been accepted for publication by PhD student Bonnie Bacchus, who has developed a reachline code. This is a code that essentially fits the path of highest intensity in a radio source. So essentially traces the path of the jet as it travels through the source, essentially. You have it summarized in this picture here. This is the link to the code itself. And you can see 2 examples here of how these reach lines are traced when you have the position of the source, when this is known. Here it's indicated with an X, but also when the host is not known. So this is something that is going to be potentially crucial, not just to identify morphological properties, which you can do in other ways, but to try and find the hosts of these extended sources, which is far from a trivial problem. And it's something that is going to become impossible to do with citizen science or visual inspection as the data samples grow larger and larger, as we have more and more sources. We find that 98% of the sources where we draw rich lines sufficiently for a sample of lots DR1 sources have the correct ID. So this is comparable to citizen science in terms of performance. So just to briefly wrap up, I'll leave you with my conclusions. The most salient points of what I have presented today is that we find that 2/3 of luminous FR2s in our deep fields LOFAR sample are lurks, which is something that is completely unexpected based on what we have seen in previous surveys. We see no visually identifiable differences between luminous and underluminous FR2s, Herg and Lurg FR2s in this regime. So you cannot tell whether an FR2 is bright or faint, or whether it's accreting fast or slowly based on visual inspection. We know that FR class is not controlled solely by jet power, because we find these low luminosity FR2s. Stellar mass is the key parameter when it comes to determining whether a low power jet ends up as an FR1 or an FR2 low. And across all luminosity and FR2 and FR classes, Hergs have a high specific star formation rate. So this is a link to fuel availability and accretion. So there's lots of ongoing work, not just from me. Particularly, I would point you to the talks on high resolution data. Vijay is going to give one. Leah and Fritz are going to present some results as well. Leah already did. So yeah, stay tuned. We have so much to tell you about so many things. Thank you.
Beatriz, thank you very much. That's a very deep and rich subject, much more detailed and complicated than what I learned way back when. I see 2 hands up right away, and I'm going to ignore Joe for just a moment and go, let's see, where is it? Christina, you have a question.
Yes, I have a couple of questions, but I'll just ask one now. So fantastic talk. This is so exciting, I think. Really a modern understanding of radio AGN. I was just wondering, in the slide you showed where you had the dependence on star formation rate. I was wondering how you measured the star formation rate, and if that plot on the right there, if it could be partially driven by redshift effects with higher star formation rates at high redshift.
Yes and no. I mean, Rohit has looked at this in more detail, as I said. So these star formation rates are derived from consensus SED fitting. We used like 5 different SED fitting codes and looked for a consensus between them. They were mostly agreeing with each other, but just to try and maximize minimize the statistics in terms of deviation. So these are drawn from both emission lines and AGN properties, and also the broadband distribution of the properties of the sources. We haven't seen any trends in terms of redshift. Obviously, because this is not a complete sample, you stop seeing the fainter sources at higher redshift, so it's not entirely complete. But I think I have, Rohit's talk here. So there is an evolution in terms of redshift here for the star-forming galaxies, which you don't see for the quiescent galaxies in terms of the lurgs. So there are definitely star-forming at even higher redshifts. Obviously, you're not seeing the complete sample there, and there is some evolution of that fraction, but you don't find that for the quiescent ones. So yes, there might be some effects, but it's very unlikely that you can start missing on HERGs rather than missing out on lurgs at higher redshifts, because the HERGs are always brighter anyway.
Okay, thank you so much.
Christina, can we go to Joe to give him a chance?
Yeah, I can ask my other one on Slack.
Okay.
Yeah, mine was actually building on Christina's question. I'm fascinated by this dependency on specific star formation rate, because doesn't it, to me, and what I learned in 101, this kind of work, right? It's one, wrong spatial scale, number two, wrong temporal scale, right? Like you would expect this, particularly FR2 activity, to have been eons before this star formation rate you're probing now. So my question was building on, are you sure there's no AGN contamination in your calculation of the specific star formation rate, because you're doing SED fitting, right? And there could be some degeneracy there.
Yes and no. I mean, we're talking about the lurgs. The lurgs don't really have an AGN there, so I don't think we're missing on. We did a fairly complete study of this. I don't think we're mistaking HERGs as lurgs in this case, because of the way we do the SED fitting. So for the lurgs, there's definitely no case that the AGN is contaminating. I was very surprised to see these results. I wasn't expecting these either. There's this famous paper by Vivienne Wild in 2010 that actually draws the timescales of when you have the star formation happen and when you actually have the optical AGN kicking in, and there is a delay, and obviously there are different timescales involved. So I wasn't expecting to see this.
Well, this is quite challenging, to be honest.
And we don't really have the information on the size of these sources, so we cannot really be more specific than having an overall specific star formation rate. But this is definitely something we will be following up with things like MANGA, for example, to try and look at smaller samples perhaps of these sources, to try and see what the gas distribution is like and why this is happening.
Cool, thank you.
Okay, well, I'm afraid, I have a few questions of my own, but we're running out of time already. So Beatriz, thank you very much.
Thank you.
And now we go to Vijay Mahatma at TLS Teutenberg, sub-arcsecond imaging of 3C radio galaxies at 150 megahertz.
Yes, thanks, Rick, for chairing the session and introducing me. And obviously, thank you to the organizers for giving me the platform to talk today. So yes, I'm going to be talking about powerful radio galaxies and what we can learn using LOFAR VLBI. So I just wanted to start off with radio galaxy models, and just want to draw your attention to the early models in the 70s, particularly by Scheuer, Blanford and Rees and Longair, who published some very pioneering studies describing radio galaxies in a very simplistic way, but sufficiently informative in the way that the jets interact with the ambient medium to produce the structures that we see today, more or less. So on the left-hand side, you can see the picture which describes how we sort of expected radio galaxies to look in terms of their morphology. So you have the radio core and you have bipolar jets, and when the jets interact with the ambient medium, you get hotspots, and subsequently you get radio lobes that form. So then came along the VLA, as the chair of this session knows all too well. And it really changed our understanding. It's purely by looking at the morphology of what can be seen at sub-arcsecond. So these are some images from Bridal et al. Paper, who did a 5 gigahertz study with the VLA of some 12 quasars. And really, when you get to the sub-arcsecond regime, the simplistic model of bipolar jets and hotspots on either side really changes when you see that, for example, there are multiple hotspots in each lobe. The extended lobe emission can be quite random at some times. The jets themselves can be resolved into multiple structures, and there's lots of bending as well. Now, this is just showing the abstract from that paper, and I just basically highlighted a few things. I didn't put this up so you could read everything, but I just highlighted a few things to just show what can be inferred from sub-arcsecond studies. And really, pretty much, I mean, I've highlighted a few things, but pretty much every sentence in this abstract is telling us something about radio galaxies that we didn't know, well, mostly didn't know prior to those studies. And so this really highlights the power in sub-arcsecond studies. And, and of course, there's been many more papers after that, well, before and after that, that show some really useful results. So given we're almost in 2022, what do we still lack in our understanding? Well, particularly when you go to a sub-arcsecond regime, hotspots can be studied quite well. Now, we know that the hotspot particle acceleration determines the electron energy distribution overall for the whole source, and that itself determines the overall jet power, which is a very important parameter for things like AGN feedback. So the question is, can we still use single hotspot injection models? You know, at low resolution, we tend to do studies of jet powers, and we use models of single hotspots. Is that robust when in reality, a lot of these powerful sources have multiple hotspots? So you can ask the question, you know, do the injection indices of each hotspot differ significantly, and which hotspot is participating in the particle acceleration at the moment? What is the origin of the secondary hotspots? How are they formed? And how does this relate to turbulence? So these are questions that really need stamping on if we are to understand radio galaxies in more detail. Of course, polarization is pretty important in order to determine magnetic field structures. So what one can ask is, okay, we know a lot about the high frequency polarization as has been done with the VLA in the past, but what can we learn from looking at low frequencies, where obviously depolarization is more prominent? So this is all pointing to the need for low frequency sub-arcsecond studies to complement what has already been done at gigahertz frequencies and beyond. So this swiftly brings me on into LOFAR. So you've heard of the LOFAR 2 meter sky survey, LOTS, which is a northern sky survey observed and imaged with the Dutch stations. What is already the case with the data is that quite a lot of the data the observations have been observed with the international stations. On the bottom left-hand panel, you can see the full European coverage of all the stations of LOFAR. So Leah, as you know, has given a very good presentation on the calibration strategy using the international stations, as well as the first LOFAR VLBI paper splash, which is now public. And some 3C sources have already been worked on by a few authors that I've put here, and have already given us some tremendous results. So I point you to these papers to look at this in more detail. So what I wanted to do is sort of look at 3C radio galaxies in general. So one of the things that we wanted to look at was to understand the polarization at low frequencies. So I did a pre-selection of 3C sources that are polarized with LOFAR at 20 arcsecond because those data cubes are available. So on the right-hand panel, you can see in color the polarized intensity of some 3C sources at 20 arcsecond resolution. So I know that if I select these sources at 0.3 arcsecond, I will see some polarization. So this led me to a bunch of 3C sources to work on. And what I'm going to be showing you in this presentation is what I've processed so far, which is 3C34 and 3C263. So these two sources have been processed using the LOFAR VLBI pipeline as introduced by Leah, as well as some further processing, post-processing using a pipeline developed by Reinhardt. So as Leah has described the processing, I'm just going to go straight into talking about the images that have come out. So 3C34 and 3C263. So these are the two LOFAR fields that have been observed with lots at 6 arcsecond. These are the two radio galaxies. So if I just zoom in, this is what you see in lots at 6 arcsecond. And after processing with the international stations and imaging with natural weighting to achieve 6 arcsecond, so similar to lots, you get this. So adding the international stations gives you a bit more structure. And then after that, imaging with uniform weighting, you see the 0.2 arcsecond resolution structure of these sources. So now you can see pretty much everything in a lot of detail. And with robust weighting at a 0.4 arcsecond resolution, and I'm just changing the color scale, you can see that there is a huge amount of structure in these sources. So I've just highlighted with arrows some of the really cool structures you can see. So just focusing first on 3C34. So on the right hand side, I've put the previous best 5 gigahertz image with the VLA of the source, just for comparison. Yes, there's double hotspots. There's a lot of complicated diffuse emission in the western lobe. There's also a long filament spreading across the base or the entire extent of the middle of the source over here, which previously wasn't seen. You also see the jet knots over here. There are, in fact, multiple hotspots in this lobe structure over here, which you can't see because of the color scaling. There's also potentially a filament running across the edge of the boundary of the lobe over here, which is not robust. I need to sort of work on this a bit more detail to confirm whether this is a filament or not. But yes, as you can see, there's a lot of things that previously wasn't seen at high frequencies. With 3C263, it's a bit less interesting, but I mean, there are no new features detected, but we do detect pretty much all the features that were detected at high frequencies, as shown on the left-hand panel. So one of the things that we want to answer, of course, is the nature of the hotspots. Now, with LOFAR, the in-band spectral indices, as you may have heard, are not very reliable because of the narrow bandwidth and flux scale issues. So you cannot robustly say what is the spectral index at 150 megahertz just by using in-band spectral indices. However, I thought what we can do instead is to, rather than say, this is the spectral index of this component and that component, we can assess in a qualitative manner what are the relative spectral indices. So we can say, oh, this hotspot is flatter than that hotspot in a very sort of qualitative and approximate sense. And so what I've plotted here are the in-band spectral indices with LOFAR. Of course, the values are a bit crazy for some of the components, but we can still assess what are the relative spectral indices of the hotspots. So on the left-hand side, you can see that one of the hotspots over here is flatter than the hotspot right at the edge. And so correspondingly, on the right-hand side, you see that this hotspot is slightly flatter than this hotspot over here. So what this kind of tells you is that the jet direction is basically going this way. And this actually matches up with the jet, which is detected at 5 gigahertz. So then you can ask, what is going on with the other hotspots? So why are they steeper? So these questions actually need sort of multi-wavelength data, which I don't have at the moment, but is still interesting to speculate. With 3C263, what you see is basically, on the left-hand side, or in the western lobe, sorry, on the eastern lobe, you see a flattening of the spectral indices at the jet compared to the core. And with the other with the other side of the source in the western lobe, what is curious is that the hotspot is over here, but there is a lobe extension surrounding the hotspot over here. And it's not currently known what is this extension. Is it just due to projection, or does the source actually go further on after the hotspot, much like in FR1. What we can infer from these relative spectral indices is that there seems to be an inverted region just over here beyond the main hotspot. So this could sort of potentially say that there is some warm gaseous environment around the hotspot region, and potentially the interaction with the source and the environment is causing this extension over here. So as mentioned, what I also wanted to look at is polarization. So this has never been done before at sub-arcsecond with LOFAR. So what I've done is just performed RM synthesis on the Stokes Q-new cubes. And you could see that with the LOFAR image at 0.3 arcsecond, we only really see the hotspot, which is polarized, which is at quite a low level, and everything else is, well, nothing else is polarized in the LOFAR image, whereas at 5 gigahertz, you see pretty much a lot of the components are polarized at a very high level at 50% in some parts. Similarly, with the 3C34, we just see that on one side of the jet, the hotspots are polarized. In fact, in this source, both of the two hotspots in the eastern lobe are polarized at the 2.5% level. And this is kind of interesting because 20 arcsecond LOFAR studies have been done for polarization in radio galaxies, only finding that you only see the hotspots that are polarized at 20 arcsecond with LOFAR. So it's interesting that at 0.3 arcsecond, we still only see that the hotspots are polarized and everything else seems to be depolarized. Just before I finish off, I just thought I'd give you a current update on the next source that I'm working on, which is 3C351. So what I'm showing you here is a zoom in of the LOTS 6 arcsecond image. And with the international stations, you get something like this, which is fairly promising because it looks like the 0.5 arcsecond image at 5 gigahertz. But just to mention that this is just a 3 times 30-minute scan. So it's a 1.5 hour scan relative to the typical 8-hour LOTS observing time. So I hopefully should be able to add some more scans into this image in the near future. So just to give a brief summary, so bright radio galaxies can be processed and imaged with high fidelity with LOFAR VLBI. We still suffer from some dynamic range issues, but more or less you can see the extended structure quite well. With 3C34, we are able to make some first order approximations into how the diffuse emission is operating. We're seeing new filaments, we're seeing extreme turbulent behavior in lobes. The turbulent behavior in the lobes of 3C34, I speculate it's more to do with the magnetic field anisotropy in the lobes rather than the environment, because the environment of 3C34 is quite sparse. And with inner-band spectral indices, we can infer what hotspots are flatter to tell us in which direction or which hotspots are associated with the particle acceleration of the jet. With 3C263, there is some lobe extension going beyond the hotspot, which is unknown, but the inverted spectral index in the lobe extension sort of implies some interaction with some warm environment that's potentially causing a lobe structure to form beyond the hotspot. The first LOFAR VLBI polarized intensity map shows that only hotspots remain polarized, but some more studies need to be done to confirm these results. And of course, LOFAR 2.0, which will be upcoming this decade, will be able to obtain broadband images at low frequencies to make these studies more robust. Thank you very much for listening.
Well, that was fascinating, seeing these new high-resolution images at low frequencies. Let's see. Joe, I see your hand is up. We'll give you a first crack this time.
Oh, sorry, I was applauding, Rick.
Oh, that was an applauding.
Yes.
That's like a hand to me. All right, we do have a hand up. Oh, yes, Etienne, bonjour. Go ahead.
I was in fact trying to.
Oh, that's another.
But I can't.
Sorry.
Sorry, my bad.
That's another clapping hand. Sorry, I'm quickly running through these things. What have we got here? Well, I have a couple questions I can throw in here. First thing is a cautionary tale. It's not at all surprising to me that the polarization of these low frequencies is so low. A recently completed study of Cygnus A, done it with the full power of the VLA, shows considerable foreground depolarization, which we are convinced is not internal to the source, but is external. But I want to caution everybody and emphasize that discriminating between internal depolarization structures and external depolarization is virtually impossible without high resolution imaging. So
yes, of course, I completely agree. So I don't try to make any inference into what is causing the depolarization, and of course, it's more about, you know, what can we actually see at low frequencies, because this has never been done before. So of course, from there we need to make more studies to try and infer what is the depolarization coming from.
All right. Do we have any hands up here? We still have a couple of minutes. I can offer another comment on the spectral index. It's always very dangerous to try to do spectral indices within band. What pair of frequencies were you using for this? And I mean, as you pointed out, the numbers are kind of crazy. Do you?
Yes, they are. Yeah, and almost certainly wrong. So yeah, so the bandwidth is 48 megahertz, and I split it into six chunks. So about eight megahertz chunks. So of course, it will be nonsense. But I thought, because you're just looking at the hotspots, so you don't suffer from sensitivity issues from the narrow bandwidth, and of course the assessment of relative spectral indices, we may to first order give some inference rather than saying, you know, these spectral indices are correct. I'm most likely underestimating the errors, which was probably also causing the very steep spectral indices.
Do you plan to combine this with the high frequency observations to get more reliable spectral indices of these structures?
Yeah. So for some of my objects, there are some Merlin observations at L band. In fact, there is a source that I'm currently working on that I haven't showed, which is 3C320, for which I have also Merlin VLA L band and C band observations for as well. So hopefully I'm going to combine all that data to get some proper, more robust spectral indices. But I don't think I have it with this source. The VLA data for these sources are very, very old and would require me to process them individually with the old VLA settings.
Yeah, well, as it turns out, in my opinion, at least the old VLA data is really easy to reduce compared to new VLA data, but that's a
fair enough. Yeah,
a subject for a different day. Any other comments before we move on? I'm spacing here, looking for hands up, but don't see any. Okay, all right. Well, thank you very much, Vijay, for that nice update and exciting new results.
Thank you.
Now we go to Zara Randriamanakoto. It's South Africa, and Zara, please go ahead.
Okay, can you see my screen?
Yes, we're seeing it well.
Okay, hi everyone. Wait, it's misbehaving. Let me first. Okay, yeah, so I'm Zara Randriamanakoto. I'm based in South Africa at SAO, and this work is conducted in collaboration with Marisa and Tubra Rivornour, a student based in Madagascar, but it also part of the MIGHTY Continuum Working Group. So today I'm going to talk about the search for remnant and restarted radio galaxy using multi-frequency surveys. We all know that when there is a typical radio galaxy, we see the signature of the activity by seeing the lobe, the hotspot, the core, and also the jade. And in that case, the total spectra of the radio source can be well approximated by a power law with an index of 0.70 usually. And following that the active phase comes the fading phase, fading period, where the source started to fade away, and we see the nebular, the diffuse emission starting to show up, and the radio source is not devoid of core and any compact source. Then following that, if the nuclear core is replenished by fresh electrons, then we start to have a new activity, and hence a new core with old remnant radioplasma. So clearly we see that there is a life cycle of the radiogalaxy tying together those three different types of radiogalaxy based on their nuclear activity. And this is why it's important to study them, because the one case before the advent of low frequency radio observation, only a handful of those objects has been detected so far, but it's also because of the fact that the fast spectral evolution, rapid scale at the high frequency, it's hard to detect it, but they are also useful since it will give us a clearer understanding on how does radiogalaxy evolve. And one important aspect also is in terms of modeling, their source dynamic will help us to constrain the evolution of radiogalaxy model in general. And when you detect those objects, when you study those objects, then definitely you should take into consideration low frequency observations, because as I said earlier, they are often very faint at the same centimeter wavelength. So here I'm presenting three different types of remnant radiogalaxies, and you can clearly see that there is this bright diffuse extended emission at low frequency. So this one at 610 megahertz with GMRT, this one 150 megahertz LOFAR by Brienza, and then the one of NGC 1534 with a Xmm telescope below 100 megahertz. So it's possible to detect these objects since the remnant radioplasma stay visible relatively longer at low frequency than at higher frequency. So, and one of the things when you observe those objects, they are mainly selected on the basis of their morphology or the ultra-steep spectrum. And also it's mostly focusing on single object. And even if there is a sample, it's drawn from that very single specific property, either atypical morphology or mainly selected ultra-steep spectrum. So clearly there is a need to create a larger representative sample so that you can better constrain the life cycle of radiogalaxy. And the following in the literature, there are, since the commissioning of LOFAR or Xmm, there has been lots of surveys, such as the one done with Lockman Hall field within a 35 square degree. It was possible to recover around 11% of remnant, and then you can see that the number varies from 4 to 11%, and for the restarted one, between 4 to 15%. How do these people to conduct the systematic search? So it's a complementary use of both morphology and spectral properties. So here I'm showing a chart, for instance, that URLIN 2021 used to select the remnant candidates. So basically it revolves around not only looking at the visual inspection, do we have any nuclear core? Are there any remnant radiolobes that are signature of all the plasma, but also use properties such as the core prominence so that you can investigate the nuclear activities of the source, or also the radio spectrum so that you can search for fresh injection. And to optimize the selection of extended source, that's when you go for angular size cut. And if you want a robust detection, that's when you go for flux density cut. And there is also the spectral curvature to identify source with highly curved spectra. So in this case, I'm going to talk about the XMM-LSS. Why XMM-LSS? Well, it has a wealth of multi-wavelength data. That is very important when you want to get the redshift of the object, either spectroscopic or photometric redshift, but it also has a wealth of archival radio data. And the choice of XMM-LSS also is motivated by the basis that it's one of the MIRCAT mighty field. So just, I'm sure by now all of you know what is MIGHTY. It's one of the large survey projects of MIRCAT, and the early science data release, you can already get it online, mightysurvey.org, but a paper by Haywood recently published introduced the data and also the catalog from Cosmos and XMM-LSS that are part of that early science data release. The XMM-LSS itself, it covered 3.5 square degree area that was taken each 12-hour pointing, so it goes down up to 6 microjansky per beam. And some papers have already been published, such as the Haywood et al. That I just said earlier, but over 20 approved early science projects as well. So one of that is the one I'm leading, which is a systematic search for remnant and restarted radio galaxy. So this is still a preliminary result, and what we want to do here is to implement the systematic search so that by the time we get a bigger area coverage of MIRCAT, we can then implement it and fine-tune. Here I'm using LOFAR, the data that was already published and available, with a catalog also available by Harl et al. 2019 against MIRCAT, with the catalog also ready with 9,000 sources. And you can see pretty well that the resolution are more or less the same. The area, as I said again, the unfortunate that the area of the current data of MIGHTY is relatively low, but we can still use it. And sensitivity, it goes down to 6 microjansky with resolution of 5 arcsecond in terms of MIRCAT data. So the LOFAR data to trace any extended radio emission, and MIRCAT data, MIGHTY survey, to recover any nuclear activity so that you can get a signature of the ultra-deep spectrum radio source. But along the way, we will also be using the other data that are available, especially those that have more or less the same resolution, such as the GMRT at 610 megahertz and JVLA at 1.5 gigahertz. So this is showing the different overlap from those survey that was published in Hall et al. 2019. How do we construct our sample, the one that we are working right now? So we consider the LOFAR catalog by Catherine, and then of course we constrain our search within the footprint of MIGHTY. So that goes down from 3,000 to around 600 sources. And then we implement a flux density cut of 40 millijansky. I'm putting this asterisk here because we are aware by putting this Jansky, we are losing out potential sources that are not bright enough, but I will get back to it later. And then an angular says cut of 35 arcsecond. Why 35 arcsecond? It's to ensure that at least there is a minimum of 5 LOFAR synthesized beam across the image, that the detected source in LOFAR. And when we look for optical host identification, we do a search and reduce of 5 arcsecond away from the first core detection. And this result, all this step, we end up with 24 sources to work on to investigate the nuclear activity of the source. So if we were to use angular says cut only, then we will start with 71 candidates. How do we split the remnant against the restarted radio galaxies. So this selection were taken from mostly by looking at the previous literature on remnant and restarted radio galaxies. So in this exercise, we mainly use three categories, three criteria: the morphology. For a remnant, are they bright and diffuse, and do we see any core hotspots? If it's not that, then most likely it could be remnant, although it also can be just because of resolution. And if it's a restarted case, we have this coexistence of active core with a remnant radio lobe, such as the double radio galaxy. We also have this cutoff of core prominence and a quite high value for the restarted one, which makes sense because we have the new core. And in terms of spectral index, if we choose based on the spectral index, then it has to be an ultra-steep spectrum for a remnant, and for a restarted galaxy, the core of that radio source, the spectral index should be less than 0.7. And these are the preliminary results that we are getting out of this criteria. So we found 4 candidates, remnant radio galaxy, and 6 restarted radio galaxy, which gives this percentage 25% for restarted, 16%, and 59%, the rest, the ones that are active. The first plot here, just giving you basically the redshift distribution of the remnant, the restarted. So you can see that most of the restarted remnant galaxy, there is still one. I think this is the one that was already published by Mahatma, but most of them are well below 1, redshift equal to 1. In terms of alpha, most of the restarted radio galaxy have spectral index between -8 and 1.0. And the 2 last plot shows the largest linear size plotted against the radio power of the source. So you can see that the remnant radio source are mostly having size that are above 500 kiloparsec, which is understandable given the diffuse remnant radio emission that they get. And here I'm showing some example of those detected remnant candidates. So this source, I call it the hippocamp. It's mostly chosen based on its amorphous morphology, but the core prominence also gives a value that is within the criteria, but it was mostly motivated by the criteria. What do we look here? So here I'm plotting first, and I'm plotting the contour is LOFAR on top of first, and then MIT on top of first. And here we see a spectral index between LOFAR and the MIRCAT data. For the case of this FR2, it's really very strong remnant candidates, no core, even at high frequency region, at high frequency data, but it also has a very steep value of alpha. So we choose it on the basis that it is a ultra steep spectral index. So it's already been studied as a single case by Tamane, and in fact, the size categorizes it as a GRG. For the detected restarted candidates, I'm showing 2 here, potentially. So this one it's still not really sure, J221, because you can see that the emission was not really resolved in LOFAR, but resolved in MIT. So you can clearly see here the capability of MIT to resolve the emission. It has been chosen based on the visual because it has a first, like this guy are from the first activity, I guess, and then the one that are just nearby the core, there are 2 little lobes, and the core, the spectral index at the core, it didn't pass, just close to the cutoff of 0.7. For J2 1847, the core is really clearly above the threshold, above 0.87, and it was not resolved again at LOFAR, but the mighty value clearly showed that there are different, that could be a sign of different activities, and that is traced in the spectral index, where here we see a steeper, but as we go toward the core, then we see flatter spectral indices. Here I was just trying to estimate if we take 5 sigma of the LOFAR, what would then be the value when it gives this, although it should be interpreted within the caution, since it's just the approximation of the LOFAR flux density. So to summarize my talk, this is a pilot study to search for remnant and restarted radio galaxy by cross-matching LOFAR and mighty XMMLSS catalog. And we've recovered so far 4 remnant and 6 restarted radio galaxy within a 3.5 square degree area. That number is more or less expected, given that there is a rule of thumb that 1 square degree, you don't expect 1 remnant, and it's possible, it's the next step that we would like to do to strengthen our analysis. So first of all, test what if we only consider an angular size cut so that we increase our source sample, but also use the GMRT and VIII catalog that are available to estimate the spectral curvature and the radio spectrum, and so that we can use BRATs to get the synchrotron age. But one thing that would really like to use also currently, there are more data that are currently being processed with the mighty area coverage. So at least it will double by a factor of 2 the coverage of the mighty. But the ultimate goal back then, when applying for mighty LSP, is to have this 20 pointings of mighty, so that it will cover at least 10 square degree area of XMMLSS. But the way to get more low frequency data is use of super mighty. So this is another project by Russ Taylor and Yogesh Wadadekar. So to image the mighty field using UGMRT, 3 and 4 bands. One of the wish lists in this project that I think would be very important and useful is to have a higher frequency that data at above 5 gigahertz, because we know that sometimes a remnant radio source, they still have a very weak radio core, but not necessarily devoid of it. A source here that I'm showing is a motivation that yes, definitely we need to increase the area coverage of mighty, or use the available radio data that is at hand, such as VLA, because as we go outside the cross-matched field, there are candidates like J0219, which is definitely a typical morphology of a remnant radio galaxy. Thank you.
Thank you, Zara. Any hands up here? We only have a couple of minutes for comment. I don't see any hands. I do have one small question. You mentioned a 5 gigahertz survey, Godfrey. What is this?
What I mean by that is that a paper by Godfrey really it has shown that the importance of using of high frequency survey above 5 gigahertz if you want to study remnant radio galaxies, because that's when you really start to pick up the nuclear radio core of your sources. So even if you have 1.4 gigahertz, it can still be missed out.
I'm not
Can you
hearing
still
anything.
hear me?
No, Zara. Well, yes and no. I'm not sure if we're alive.
Yeah, I think we're all fine, Rick. It might be on your end if there's an issue. I can hear it fine.
Yeah, no, I can hear also. So I think we're back.
Yeah, I think maybe you just had a bit of lag.
Okay. All right. Well, unfortunately, Zara, we have to move on. We've reached the time. And so this brings up Marisa Brienza, who has a presentation on Filamentary AGN Remnant Radio Emission in the SKA era.
Yes. Can you hear me?
Yes, we can.
And can you see my screen, full screen?
I can see it.
Perfect. Thanks a lot then. Hello, everybody. So my name is Marisa Brienza. I'm a postdoc at the University of Bologna. And yes, thanks a lot for giving me the chance to present our work today. In my talk, I will actually continue a bit the discussion on remnant AGN plasma started by Zara before me. And I'll just remind here that when we talk about AGN remnant plasma, we refer to the plasma which is left by the AGN once the jets switch off or move away. And this plasma naturally tends to expand in the surrounding medium and also to radiate away its energy. And in this case, the spectrum, the radio spectrum becomes scarce and steep at high frequency. And this is why it is optimal to observe and to search and to observe these sources at low frequencies. And in particular, there are various reasons why we want to study this remnant plasma. For example, the modeling of the radio spectrum can help us getting constraints on the timescales of the jet activity, which is of course relevant for understanding the jet AGN triggering and at the same time quantifying AGN feedback. And by following this plasma on long timescales, we can also prove the physics of the AGN feedback better. And last but not least, we can explore how much these jets enrich with mildly energetic particles the surrounding medium. And today I will focus mainly on this last point here. Indeed, while people, I guess, had always imagined this, observations in the last years are really starting to routinely probe how radio galaxies inject plasma in the surrounding medium and how this plasma interacts with the surrounding medium. Moreover, we can really now observe how the AGN remnant plasma can travel very large distances and overall how it can permeate the entire intragroup or intracluster medium. And all this is also pushing a lot simulations in this direction. As you can see on the right, there are a couple of examples. And in particular, thanks to the high sensitivity and resolution of current observations, especially at low frequencies, but not only, I have to say, we can really start appreciating all the fine substructures of this plasma, which are really becoming very, very common to date, with very impressive filamentary features and whose origin are still under debate, I would say, but which can surely teach us a lot about how this plasma evolves with time and also how it interacts with the magneto-ionic surrounding gas. And here I'm just showing you a few other pictures, a few other images of some nice sources, which are actually well known in the literature, but where we observed just recently much more emission and filamentary emission with low surface brightness and also signatures of interaction with the surrounding medium. So here in particular, you can see on the left some old images at higher frequency, and on the right some more recent LOFAR images at 150 megahertz on the right. Yes. And all this can be relevant also for in the context of the study of diffuse radio emission in galaxy clusters. Indeed, the fact that this AGN remnant plasma is really observed to permeate the surrounding intracluster, intragroup medium really suggests that it may play a role in providing seed particles for the formation of diffuse sources such as relics, halos, and mini halos, which, as you most of you know, are not associated to an individual galaxy, but are large-scale diffuse sources which are related to the dynamics of the system, like shocks or turbulence, for example. So with this introduction in mind, I will now focus on a specific system and galaxy which we have been studying in the last months, which is NGC 507. And here I will give you a short overview of it, first of all. So this is a galaxy group and located in the local universe at redshift of 0.016. And its mass is about 6 × 10⁻13 solar masses. And in the bottom, you can see the optical image with marked some of the galaxy members in as pink circles. It contains about 80 galaxies, more or less. So associated at the with the central elliptical galaxy, there is a already well-known radio galaxy with FR1 morphology and extending for about 70 kiloparsec and very low power with more or less 10 to the 24 watt per hertz at 150 megahertz. And this was already studied in the past, as I said, and classified as a remnant or dying radio galaxy because of the lack of compact features like jets, for example, and cores and core, but also but mainly actually because of its very curved spectrum with spectral curvature of about 1.5. And previous authors estimated an age for this double source of about 140 megayears in total. The system is also very well studied in the X-rays already. Here I'm showing you some Xmm observations. So in particular, the X-ray luminosity is about 1 × 10⁻43 erg per second. And the X-ray morphology is pretty peculiar. It mainly consists of two components, one inner component made of mainly two peaks of emission. The main peak is coincident with the central galaxy or also with the central region of the group. And the secondary peak is slightly on the west side, and it's interpreted as due to a compression of the gas due to the interaction with the western lobe of the radio galaxy. Surrounding this central X-ray central emission, there is a halo of diffuse X-ray emission, which is asymmetrical. As you can see, it is more extended in the north with respect to the south. And moreover, we can clearly see and recognize two discontinuities in the X-ray emission, one on the east side and one on the south, with a very peculiar arc shape. And in particular, the one in the east was already extensively studied by Kraft and collaborators in 2004, while the southern one was a bit less characterized in the literature. So with this, let's say, introduction in mind, let me introduce you to our new LOFAR image at 144 megahertz. Here you can see a combination of radio emission in red, but also blue emission, X-ray emission in blue and STSS in background. Here, all the main features that I already told you about before are summarized, but on top of that, you can really appreciate how we now detect this very extended low surface brightness emission on the bottom right with the very much filamentary morphology. And this emission is connected with the eastern lobe of the galaxy, in particular through a very thin and thin filament of emission. And so we interpret this as remnant emission from a previous AGN outburst, which was previously undetected. And the most striking part, I would say, is that this filament has a S shape, an arc shape, which is very nicely following the southern discontinuity observed in the X-ray. So we further observe this source with the GMRT, with the GMRT at 400 megahertz and 675 megahertz. And here you can see all the images that we collected, and in particular on the top, in the top panels, you can see the high resolution images that we produce, where you can really appreciate the fine details of this emission. And in particular, you can really see this filament in the south, which is very well recovered both with LOFAR and with the at 400 megahertz mainly. And in the south, in the bottom, actually, you can, in the bottom panels, you can see low resolution images where you can better appreciate the overall extension of this emission. And as you can see, when going at 600 megahertz, already the diffuse emission is disappearing, and this is due to a combination of sensitivity, but mainly because of the steep spectral index. And so here, let me go to the radio spectral analysis that we performed first on the main double lobes, the ones that were already known before. And here we confirmed through radiative age models, we confirmed an age of the double source of about 150 megayears. And we computed for a first order estimate of the extended, newly detected extended emission of about 300 megayears. And here you can see the spectral index map produced between LOFAR, so 144 megahertz and 400 megahertz at both high and low resolution, where flat means, let's say, young, and it's in blue, and steep means old, and it's in red. You can see that already the double lobe have a very steep emission with about a spectral index of about 1.5 more or less, and quite uniform distribution. But of course, much steeper is the newly detected remnant emission with values which can reach up 2.5 and even more. Within the double lobes, the spectral distribution is quite uniform, and also in the newly detected remnant emission, we don't really observe a clear trend, and also in the filament, we don't really see any flattening, for example, which would be maybe expected in case of a strong compression happening in that place. We then also reanalyzed the X-ray data, in particular XMM data. And here I'm showing you on the left the X-ray image, the X-ray residual image with a beta model subtracted, and on the right a X-ray image with a filter, with a GGM filter. And in both cases, you can really appreciate how now the discontinuities both in the eastern and in the south are really enhanced. And also we can clearly see a spiral structure in the emission of the gas. And we also produced profiles in the direction mainly of these two discontinuities, and we observed the surface brightness drop as expected, of course, on the left. And in correspondence of this, we observed a slight temperature increase, which is, let's say, typical of cold fronts, that is contact edges between regions of gas with different entropies. And of course, we are talking about a galaxy group, and these two phases of gas are coming from the same, let's say, group gas, which is redistributed. So it's not as much, these features, these jumps in the profiles are not as much high as those that we observe in galaxy clusters, where the two media are coming from the two merging clusters, for example. Overall, the presence of these cold fronts shaping a spiral morphology are suggestive of sloshing happening in the system. And in particular, following simulations, the spiral morphology is indicative of sloshing with a perturber located in the plane of the sky. And here I'm showing you also the X-ray spectral maps that we produced to study the distribution of the properties of the gas surrounding the radio galaxy, in particular the temperature, entropy, pressure, and metals. And also here you can see an asymmetrical distribution with a spiral pattern, especially in temperature and entropy, and clear temperature discontinuities. The pressure and metal maps are a bit more difficult to interpret due to the multi-phase gas with very similar properties. However, we can say that we don't really recognize any clear abundance front in correspondence of the eastern discontinuity, as was previously suggested by other authors. So in conclusion, what we think we are observing here is a remnant AGN plasma, which is probably transported by sloshing motions during its buoyant rise in the group atmosphere. This plasma is probably not really mixed with the intragroup medium yet, and the filament is likely tracing some enhancement of particles which are accumulated in that position following the velocity fluctuation of the intragroup medium. We also computed the first order estimate of the sloshing time scale, which we found to be around 150 mega years. And I remind you that remnant plasma we estimated to be 300 mega years old, not megahertz, sorry. So this is consistent with the idea that first the remnant plasma was produced and injected in the surrounding medium, and then the sloshing started to operate and move and transported away this plasma. Together with the sloshing, we cannot even exclude that other interactions with smaller systems are, let's say, shaping the morphology of both the radio and the X-ray emission. And in particular, if you look at the bottom left panel, taken from a simulation from Batza and collaborators in 2021, we can see that these, let's say, arc-like pictures can be produced by an interfering system moving from the south to the north. So understanding the perturber in this system, the perturber initiating the sloshing remains a bit difficult. We performed a variety of optical tests to do that, to understand that, but let's say none of these are conclusive. However, the main candidates remain NGC 599 and NGC 508, which are pretty close by. And in the case of 499, the low magnitude different with NGC 507 suggests that it may be able to produce such a perturbation. So overall, NGC 507 probably represents today the clearest example of Agn remnant plasma transported by sloshing in a galaxy group. To my knowledge, there are other few groups where cold fronts are observed, which I'm listing here, but only in one, which is NGC 5044. Some remnant plasma is also detected in the system, despite a lower resolution, I would say, and sensitivity. So overall, this system is a beautiful example where we can really appreciate how also in galaxy groups, the Agn remnant plasma can get transported away from the original position and likely dispersed throughout the entire system. And these particles are the same particles that in more massive clusters, in more massive systems, would probably be important for the creation of diffuse sources, as I mentioned at the beginning. So overall, I just say that new generation instruments are pushing the study of remnant radioplasma really forward, and in particular, low frequencies are really allowing us to trace the evolution of this plasma up to very long time scales and distances, and even now in low mass systems like galaxy groups. And high resolution and sensitivities are really key and are really giving us access to a new regime where all these filaments are coming up and are surely will teach us something about also the properties of the surrounding medium. And overall, this will help us surely make some steps forward in the our knowledge of AGN feedback and diffusers in galaxy clusters. Thanks a lot.
All right, thanks very much, Marisa. It was fabulous images there of NGC 507. Do we have any comments here? Any hands raised? Any hands raised? I have a question. So that arc in 507, that second last image you showed there, it looks perfectly parabolic to me, almost like it was some sort of orbital motion. But you're saying this is a sloshing phenomenon, or do I misunderstand your conclusions?
So the idea, if I can get back, maybe, no, sorry, I made a mess. Sorry. So the idea, sorry, do you still see the slide?
No, I'm only seeing all the people right now.
Okay, sorry, then I'll just talk. So our idea is that because of the spiral structure that we observe in the X-ray, we are likely seeing some sloshing motions in this system. But the arc-like structure, the arc-like features in both observed both in the radio and actually coincident with the discontinuity in the X-ray might be related to some, let's say, passage of let's say a second not cluster, sorry, a second group, a second clump, moving from the south towards north. And this, according to simulation, would create this, let's say, enhancement of particles in this position. So let's say a combination of sloshing with some probably smaller interaction with some other system. But if you have other ideas, I'm welcome to listen.
And I guess it's given that extraordinarily steep spectrum was at 2.5 or something, really amazing for such a thin, what seems to be such a thin filament, at least to my eyes. I guess it's useless to consider going to high frequencies to get more information.
Yeah, I mean, it would be good. This is something we still don't have observations at higher frequency. The highest we have are the 600 megahertz with GMRT, but the sensitivity is not enough due to detect this structure due to the stiff spectrum. So yeah, and polarization would be also good, for example, to see, but same problem.
I was going to mention polarization, but at these frequencies, it's a tough game.
Yeah, so we should get very sensitive observations at gigahertz frequency, let's say.
Okay, well, I regret to say that we are out of time for Marisa.
Thanks a lot.
Thank you, Marisa, for that very interesting talk. And now we go to Marie-Lou Gendron-Marsolais, who has a presentation on a source that I know well. What can bent jet radio galaxies teach us about clusters of galaxies? Go ahead, ML.
Yeah, just 1 second. Okay, can you see my slides?
Yes.
Is everything all right?
Picture.
Excellent. Yes, thank you. My name is Marie-Lou. I'm currently an ESO fellow. I'm spending the last year of my contract at IAA in Granada. I moved actually last week. So I'm going to give you today an overview of the deep multi-scale low radio frequency observation of the Perseus cluster that we have obtained with the VLA following the expanded Very Large Array project, so after 2013. But I will focus on this talk on these 3 bent jet radio galaxies that are inside this cluster that are very interesting. But all the results on this observation are summarized in these 3 papers. And I want to highlight here that all of this work have been done in close collaboration with Julie Lavacek-Larando and her group. She's my former PhD supervisor and now very close collaborator. And she was originally supposed to present at this conference, but couldn't attend. So I want to say that without her incredible intuition for forefront projects, all of this would not have been possible. So go check out her website and the work of her group. So I'm going to talk about the Perseus cluster, right? And maybe some of you don't know this cluster in particular. So it's the X-ray brightest cluster in the sky. It's very nearby, only 70 megaparsec away. And so this is key because it's so near that we see a lot of detail in that kind of cluster. It is a cool core cluster. You see this peaked X-ray distribution here in blue, produced by the intracluster medium, which is this hot diffuse X-ray bright plasma. And in Perseus, you also see these beautiful cavities, these pair of cavities showing the AGN feedback mechanism. And all of these have been inflated by the central AGN here, which is located in the brightest cluster galaxy, NGC 1275. So that's just a very quick summary of the Perseus cluster. Now about the data, so it's all VLA data, as I said at the beginning, in two different bands. So 350 megahertz, the P band here, and the L band 1.5 gigahertz. So why going to low radio frequency? Why we want to study cluster at low radio frequency? Well, we've mentioned this a lot during this the last few talks, but obviously because of spectral aging of the synchrotron emission from the particles released by the AGN jet. So when you go to lower frequency, it really gives you access to the less energetic particle population that you will find spreading around all the clusters or groups of galaxy, apparently. That's very exciting. So in terms of work, I've been working on the P-band observation. So I've done the whole process from data reduction to the analysis. But for the L-band, I want to mention that this has been a lot of work done by Chad Hall and our chair, Rick Perley. They have been working very, very hard to produce these beautiful images at L-band. And I know how much work it takes to do this. So it's very hard to image Perseus because it's the central source, the central AGN 3C84 is extremely bright. And so it just tends to outshine everything next to it. And so you have to be able to reach very high dynamic range to be able to see the faint emission right next to this extremely bright source. But we've worked a lot and we managed to produce these maps here where we see a lot of things. In the center right here, you have 3C84. It's very small here, but you see the tiny radio jets of the BCG, and then around it kind of embedded, it's all embedded inside the mini halo emission, which is this diffuse central part here. So we've been able with those observations to resolve interesting structures in both cases, in the radio jets, but also in the mini halo. But I'm not going to focus on that today, so I invite you to see these publications if you're interested about that. So I'm going to focus on the Benja radio galaxies, which are these peculiar source. We have 4 of them in the Perseus cluster, all with very different morphology. So it's a very nice laboratory to study these kind of source. So what are Benja radio galaxies? Well, they're normal radio galaxies with normal radio jets, but they are traveling through a cluster of galaxy, or they are encountering some strong intracluster medium motion, and so their jets are going to be bent by the ramp pressure. And so the higher the velocity between the galaxy and the intracluster medium motion, the higher the ramp pressure and the more bent the jets are going to be. Now, historically, we've been sort of classifying these sources based on this here. So basically on the degree of bending of the jets. But I would say that with the recent advances in sensitivity of low radio frequency facilities, I mean, we've been revealing more complex and unusual structure with these sources. And that has been really kind of challenging this original classification. And we've seen this in many of the talks today. I'm just thinking about for example, the Meerkat Galaxy Cluster Legacy Survey, where they seem to be finding lots of weird radio galaxies. And I'm sure we're going to see that in the next talk as well. And this is just going to get worse, right? Because, for example, with the first survey that SK is going to do, we expect to find something like 1 million of Benja radio galaxies. So it's going to be very challenging to classify these sources. And if we just come back to this very simple example of NGC 1265, even then it's kind of complicated. Even if this source is kind of considered as one of the prototype of these Benja radio galaxy. So if you just look at this image, it kind of looks like this cartoon here, a narrow angle tail radio galaxy. But if you had only, let's say, high resolution observation of this source, but that are not deep enough, or that are not, the dynamic range is not high enough, then you would only see those collimated part of the jet, and that would look like more like a wide angle tail, right? On the other hand, if you look back at the first radio images of the Perseus cluster, then you don't have the spatial resolution to resolve these jets, and that looks more like a head tail. So just with this example, it's very hard to classify it. And I want to point out, this was pointed out also previously, but this idea of redefining our classification of radio galaxies, there was this very interesting idea, I think, by my collaborator Larry Rudnick, of instead of trying to fit those galaxies inside boxes that are in the end maybe not so well defined, we could assign them labels or hashtags, for example. So I really like this idea. Now things get even more complicated for this particular source when you look at it at lower resolution, when you pick up more diffuse emission. And then you see this much fainter extension of the tail that kind of bends on almost like a full circle. This was known before. We knew about this tail before, but with our observation, we were able to resolve filaments even in that part here of the tail, which again, it seems to be really things that we see everywhere right now in all of these radio sources. There's like filaments everywhere. Now, it's very difficult to interpret based only, if you think only on the host motion inside the cluster, or if you think about some very crazy projection effect. It's not simple. I think it's pretty impossible to explain this morphology based only on that. I think it requires for sure some level of interaction between this source and the intra-cluster medium. And this was actually proposed in this paper here, where they suggest that it has passed through a shock wave inside the intra-cluster medium. So that's interesting, but it's a bit hard to test for this source because it's pretty far from the cluster center. It's like 600 kiloparsec far in projection. So there's not a lot, the ICM density is not very high, it's not very bright, so it's a bit hard to probe what's happening there, even though there's more and more results about what's happening in the outskirts of the Perseus cluster. But I would say that there is more and a more easy, or let's say, yeah, kind of easier case I will talk about just a bit later in this talk. Now, as I said, there's several one. I've just mentioned 1265. Now, another very interesting case is IC310, which was originally identified as a head tail. And then when you look at it with sufficiently high resolution, it really looks like there's a gap here. So this looks like two very narrow collimated distinct jets. And we confirmed this as well with other observations that were available. So this gap seems to be real. So that was quite interesting, although there is this slight complication that there is very high energy emission coming from that source. So gamma rays, very high energy gamma rays that are coming from IC310. And so for these people, IC310 is a blazar. So with one jet pointing towards us, it's not at all a Benja radio galaxy. So how do we manage all of this? Well, we came up with an idea that agrees with both of these observations, and it comes down to the fact that the radius of curvature of these jets is very, very small. It's kind of too small actually, and we think that this might be a projection effect. That IC310 is more like a narrow angle tail radio galaxy, but seen sort of edge on, so that the jets appear much closer to each other. And in that way, I mean, if we're looking in this direction, we would still see these gamma rays, right? Because they are probably coming from a part very, very close to the supermassive black hole, so not following these bendings, so they would come anyway towards us. And so with all of these results, we think that blazars and Benja radio galaxy might actually not be mutually exclusive phenomena. And IC310 would be like the first case of that. Now there's another head-tail source in the Perseus cluster, which is much more thin, CR15. In this case, I mean, it's very, very thin, so we don't resolve any double jet structure in IC310. Now, head-tail are very interesting and very mysterious. I think I'm not convinced that, you know, all head-tail, if you resolve them, you will see two jets, or I'm not sure. Like, I'm not sure if all of them are actually edge-on Benja radio galaxy, because then would that mean that we would see gamma rays in all of them, I guess. So I'm not convinced that this is the case. And in any case, there is still this very important question of how some of them seems to be, you know, staying collimated on very, very long distances, such as this beautiful example in this cluster that we had a great talk about earlier today. So are all head-tail the same thing, or is there like fundamentally different subclasses inside a head-tail radio galaxy? I don't know, but I think it's a very interesting topic. Now, for the rest of the talk, I'm going to talk about 1272, which is the most recent results, which is completely different, like a very not collimated case, I would say. So using these L-band observation at very high resolution, we found some very interesting feature related to that galaxy, which we knew which was identified before as a wide-angle tail. So we could only see this kind of boomerang shape jets here, which are the brightest part, located just here at the very end of the mini halo. But with this resolution, we were able to resolve out part of this mini halo into a complex extension of the Benja of that galaxy. So all of this seems to be linked to that galaxy. So you have this winding channel here that is connected to the jets. It evolves into this eddy-like structure, and then there's those more diffuse lobes here. Now, that's very interesting, and I think it's quite likely that the electrons coming from that galaxy are contributing to the mini halo emission that we are seeing. And such connection have been seen, you know, we're seeing this more and more, for example, connection with relics, for example, and there's this other case, another mini halo with a Benja radio galaxy that is very near. So the possibility that Benja radio galaxies could contribute to diffuse non-thermal emission in cluster may actually be a general phenomenon, and that it's only now that we're starting to resolve these things out. In terms of interpretation of the structure, it's a bit complicated. So we have in our paper, we kind of suggest many different things. I'm not sure if one is the correct one, or if there's the combination probably of all of those. One of them is, for example, a mixture of the orbit of the galaxy and some projection effect. Because when we look at Benja radio galaxies, often we see ones that are kind of incoming inside a cluster and others that are outgoing. So this one could be sort of an intermediate case. And so that we could be capturing this galaxy as it is turning around on its orbit through the cluster. And in this way, we could see, like in a projection, we could see the Benjets here projected in front of the rest of the tail, because this morphology is a bit strange, right? So, so with this projection effect, it could explain this. Another important point to note when we overlay the X-ray emission on top of all of this is the presence of that discontinuity here in the intracluster medium, this cold front, that really matches the position between the more collimated part of the tail, I would say, and the much more diffuse part of the tail. And so we suggest that perhaps a passage of that galaxy through that discontinuity, through the cold front, could be responsible for that transition. And finally, I think there is striking similarities between those structures here and Kármán vortex street. So these structures are characterized by a repetition of swirling vortices, and we observe this in nature on various scales. But the important thing here is that these structures appears only in particular condition in terms of the viscosity of the medium. And so if the electrons are coming from that galaxy and are following the wake of that galaxy through the cluster and form vortices like that, that would mean that we would be constraining the transport coefficient of the intracluster medium, which is something that is currently quite hard to estimate based on the X-ray observation. So a very interesting idea. So in conclusion, I think that with the level of quality that we are now reaching with observation of Benja radio galaxy, we're realizing that there's a lot more we need to understand about them. And Persis is, of course, a very good laboratory for that. And we're going to have, I'm working currently on higher frequency observation of this cluster. I think we're going to find many more things. There's also other VIII observation of nearby cluster that Julie and her student are working on. So stay tuned for those. And but I hope that one day with all of this, we can use Benja radio galaxies to probe, to use them as tracer of the cluster weather. But I think for this, we need to rethink our classification method. We need the support of simulation as well to better understand the link between ICM bulk motion and the effect on those tails, and of course much more observation. But all of this effort, I hope, will pave the way to for future radio telescopes such as NGBLA and SK. So feel free to contact me if you got inspired by this observation and want to help me understand them. Thank you.
Thank you, Marie-Lou, for such a beautiful presentation of beautiful data. And I'm not just complimenting myself here. Do we have Joe? I see your hand up. Go ahead.
Yeah, I was interested. Great talk, Marie-Lou. I just had a question about IC310. How confident are the gamma ray? So I think your interpretation is probably correct there, where you're seeing like you're pointing into the jet and you're seeing it sweep back in the radio. But how confident are the gamma ray astronomers with the association? Because obviously it's a dense environment, a galaxy, like. And it looked offset to me. Like, how confident are they? Association.
Oh, maybe the image I showed you was not. So this is 1275. This is the cluster center.
Okay. Yeah.
And this is IC310. So it's definitely not.
Right, yeah, that looked much more confident than I had misunderstood. Sorry. Yeah, thank you.
yeah. I should probably like change the image a little bit.
Further away galaxies, you know.
Yeah.
NGT names.
Yeah. I'm not I don't know much about gamma ray emission, but I think they're pretty confident.
Yeah, that looks pretty confident now to me.
Yeah.
I just didn't understand news source there. I thought. Cool.
Yeah. No, thank you for the question.
Any other hands up? While we're waiting, I can ask, what is the status of the S and C band observing of CSA? I don't recall if I'm involved in this or not. So
I think you are. I think you are. No, but it's very much in progress. Yeah, I'm just struggling with the imaging and the calibration and all of that. So it's gonna take some time before I get some results.
All the data has been taken?
All the data are yes.
Okay.
So it's just the work coming. That's gonna be challenging. Yeah, I'm gonna need help. So
well, if I could clone myself, I'd offer my other half to you for this, but I'm afraid not. Okay. Do we have any other hands up here? If there's any,
there is someone there. Yes.
Go ahead. There. Yeah, Hoob, go ahead.
Okay. Hi, Rick. Good to see you.
Yeah, it's not good to see you.
Really beautiful images. I really enjoy this. So one of the big questions in the field is, what is that synchrotron plasma made of? Electrons, sure. Positrons, protons, something else? Are the images not nice enough to really say something on this?
About what? I missed the first part of the question. Sorry.
So that synchrotron emission comes from plasma, and of course there are electrons there. But is there anything else?
I don't know.
He's asking whether or not the charge neutrality is from protons or positrons or something else, I think.
I
Thanks,
have
Rick.
no idea. I have no idea. Is there a way we can know that with those observations? I have no idea.
Let's leave it there because it's
Yeah.
the protons there. You expect different dynamics, for example.
Okay.
Yeah, polarization would help, but that's again a tough thing.
Well.
All
Gotta work on
right.
that.
Wouldn't you get gamma ray emission if there were protons?
No, not with that low density.
Yeah.
Okay, well, I'm afraid, Marie Lou, we're going to have to let this go at this point and move on to the last talk of the session, Andrea Botteon, the LOFAR Galaxy Cluster Deep Field.
Hello, everyone. Can you see my?
Yes. Yep, we're looking good.
Is it full screen? Oh,
No, it's the whole screen right now.
Let me try again. Okay.
That looks better. Yes, go ahead.
Hi, everyone. And I am Andrea Botteon, and I am a postdoc researcher at Leiden Observatory. And today I'm going to talk to you about the LOFAR Galaxy Cluster Deep Field, a work that has been done in collaboration with many persons in the LOFAR Galaxy Cluster Working Group and Survey KSP. So we had some excellent talks on Galaxy Cluster. I would like to start with a picture from simulation of Galaxy Cluster mergers. So we know that cluster form through a hierarchical process where they accrete their mass across cosmic time. And mergers between galaxy clusters are the most energetic events in the universe, and they release up to 10 to 64 erg in the intracluster medium on timescales of a few gigayears. And the largest amount of this energy is dissipated by weak shocks and turbulence in the heating of a gas, of a thermal gas, but a small fraction of this energy can be dissipated also in non-thermal components, so in the acceleration of relativistic particles and amplification of magnetic fields. Here you can see the images from a simulation kindly provided by Franco Vazza, where you can see the energy flux dissipated by shocks and turbulence in a massive galaxy cluster. As you can see, the energy is dissipated over large scales. This panel have a size of 8 × 8 megaparsec. And you can see that shocks and turbulence have different morphology. Shocks are more filamentary, while turbulence is more volume filling. And of course, shocks and turbulence coexist in the intracluster medium. So we can combine these two images and obtain an image of this kind on the right, where you can see the energy flux dissipated by turbulence and shock in the same panel. So in this case, you see less filamentary structure in the central region, just because we applied a more aggressive cut on the shock Mach number. So overall, the intracluster medium is filled by simulation tells us that the intracluster medium is filled by shocks and turbulence. And the fact that this motion can accelerate particle and amplify magnetic field is proven by radio observation of radio halos and relics. For example, here on the left, you can see a nice picture of the Able 2744 system, where we detect a radio halo in the cluster outskirts that is associated with a shock, while in the central region, we detect a radio halo that is associated with turbulence. Overall, this observation sample a small region of the cluster, so the innermost region, but if you check in the size of 1 megaparsec in this panel is relatively small compared to what a galaxy cluster is. And the fact is that what is outside the innermost regions is largely undexplored because of limited sensitivity of the current instrument. We can't see these motions in the X-rays with the current instruments, the shocks and turbulence. But if these motions are present and they dissipate part of the energy in non-thermal component, even over such large distances, maybe with radio observation, we can hope to detect this complex nature of shocks and turbulence motion. That's why we observed a galaxy cluster with very deep sensitive observation at low frequency with LOFAR, that has been already introduced these days. So a brief recap, LOFAR is an interferometer built mainly in the Netherlands, but spread all over Europe. That is an ideal instrument to study extended low surface brightness sources with steep spectra, such as the non-thermal cluster emission. LOFAR operates in two frequency bands, with the LBA in the band 10 to 90 megahertz and with the HBA in the frequency range 120, 168 megahertz. So we had to decide which galaxy cluster to choose for a deep field, and we chose the Abell 2555, which is a nearby galaxy cluster. That is one of the earliest cases where a radio halo and a shock and a radio relic were detected in the intracluster medium. You can see that this cluster is very complex, has a lot of structures. This is the image that we published last year, that is based on 8-hour observation carried out in the context of a LOFAR 2-meter sky survey, so at 144 megahertz. You can see the halo, the relic, plus a number of tailed sources. As this cluster has bright redshift to be imaged very well with LOFAR, it is in a perfect region of the sky in terms of the declination and also in the, let's say, field. We have recently observed it with deep LOFAR observation, so 72 hours observation with LOFAR LBA and 72 hours observation with LOFAR HBA. And these are the subject of this talk. I anticipate that by the end of 2023, this cluster will be observed even for more time with the HBA, and we will accumulate about 300 hours in HBA. But this talk is based on these 72 plus 72 hours observation, and I will show you the images in this slide. And these are really the deepest images that we have ever obtained on a galaxy cluster at low frequency. On the left, you can see the LBA image. It has a central frequency of 49 megahertz, and it has a resolution of 20 times 12 arcsecond, and it has a noise of less than half millijansky per beam. This is quite amazing, I would say, and it's possible thanks to the improvement done in the last years on the calibration of low frequency observation. On the right, you can see the HBA image at 145 megahertz. The resolution is about 8 times 5 arcsecond, and the noise is 43 microjansky per beam. What these deep images tell us is that the cluster is embedded in an extended low surface brightness emission that is embedding basically all the sources that were previously known in the system. And this envelope is confined in this contour, which is basically the 60 arcsecond resolution source subtracted image, and it's highlighted by these arrows, and is detected despite the fact that we are looking at high resolution images. So this emission is really giant. If you look, this is the scale bar. This is 1 megaparsec, and this means that the emission from year to year covers a projected largest linear size of about 5 megaparsec. And to give you a context on the size of this giant emission, I will show you some composite images. So this is the SDSS image of Abell 2255. The cluster is at the center of the image. Here in blue, it's the X-ray emission detected by Rosette, so the hot gas that is permeating the cluster. This is what we observed with LOFAR, and we observed in the past, so a nice radio halo that is sitting on the top of the X-ray emission, plus a relic and the tailed sources. But when we go deep and also at low resolution, so we increase the sensitivity to low surface brightness emission, we see that all these structures are embedded in this giant emission that is reported in purple in this image. Overall, this emission covers a projected area in the sky of about 20 megaparsec square. And to give you an idea of the size with respect to the size of the cluster, this circle here is R200. So it's basically the viral radius of the cluster. And this means that we are detecting the radio emission, diffuse radio emission up to and beyond the viral radius. The interesting fact is that we are not only detecting this diffuse emission, but we have also enough signal to noise to map its spectral index, as you can see here in the plot on the right. The spectral indexes span a wide range of value, and this image has been obtained with source subtracted. So just the extended detailed AGNs are kept in the spectral index map. And I remind you also from what has been said in previous talk that generally shocks tend to produce flatter emission, which is localized at the location of shock fronts, while turbulent motion tend to produce a steeper emission, which is more volume filling. The fact that we are detecting emission up to R200 is very interesting because we are starting to probe an uncharted territory of what is called the infalling region. Indeed, if you compare this image to this image from a numerical simulation, here the colors are the X-ray brightness, yes, of the cluster. You see that in the R200, within R200, we are starting to see the infall of matter in the cluster, the aggregation of structure, and the accretion of matter in this infall region is likely to generate the shocks and turbulence that are generating the diffuse emission over such large scales. To do a more quantitative analysis of the spectral index, I produced this spectral index map with independent pixel, and that's why it looks more pixelated than before. Here I blanked the emission associated to the tailed source. So on the right, I reported the histogram of the spectral index measured in this map. As you can see, the distribution is not uniform, is not even Gaussian, but I can't tell you if it is bimodal or trimodal. Of course, here I reported a bimodal distribution, and it seems to describe quite well this histogram, but actually we can see also three peaks if we want, right? And there might be a peak around 1, another one around 1.3, and another one around 1.9. The interesting fact is, even if there are three peaks, we have an intuitive way to establish what is the reason of these three peaks. Indeed, the flat spectrum emission in the cluster should be associated to the fronts of the relics, so basically where particles are flashily injected, while the steepest spectrum emission is essentially due to the large emission that we detected with the new deep images. Instead, the intermediate spectral index are due either to the emission of the halo that was reported by previous observation, but also to the downstream region of relics where particle age. And so the interesting thing is that these deep images not only are allowing us to prove the diffuse emission in new regimes, but with the spectral index analysis allow us to disentangle also the processes that generate emission, that are shocks and turbulence. So changing the resolution, these are the images that I like most. Here I show you the high resolution LBA and HBA images. On the top right, you can see the resolution and the sensitivity, and you can see that this cluster in the central region is very rich of structure. And I want to pinpoint some of these in the HBA image because it has a high resolution, starting from the central region where there are these thin filaments of emission associated with probably this head-tail radio galaxy and this other source that are still under investigation. One of the most prominent radio galaxy in Able 2255 is this radio galaxy here, which is called the Beaver. It is 1.3 megaparsec long, and it has this wobbly structure. And as Marilu mentioned 15 minutes ago, these structures are possibly instabilities generated by the jet while the galaxy is moving cluster outskirts and generate what is called Karaman vortex strait. In addition to these very giant radio galaxies, there are a number of smaller radio galaxies embedded in the emission that are highlighted with these red boxes. And these radio galaxies are either tailed AGN, but also they are star-forming galaxies that are infalling in the cluster and that are being stripped while they are moving in the intracluster medium. There are other filaments associated with this region here that is not clear if they are associated with this radio galaxy or to the intracluster medium emission. The two spars of emission here instead are likely due to the intracluster medium. There are other three straight filaments in this region of the cluster that form this kind of box-shaped region, which appears very different in LBA. Indeed, in the LBA image, we don't see very well this structure because of spectral index reasons, but instead we see that the emission is more bumpier. If we combine these high resolution images, we can obtain a high resolution 12.5 arc second resolution spectral index map between 50 and 150 megahertz, which is quite amazing. Here you can see this map on the right, where you can see that there is this mixing of tailed and diffuse emission in the cluster center, and this prominent bump in the LBA is this region in the spectral index map, where the spectral index is very steep, above 2. And we also see some flat spectrum emission that is not associated with radio galaxies. For example, for this spar, you can see that this filament has a spectral index of about 1, but especially this region of the free filament here has a spectral index of about 1. And this region is interesting because in the VLA observation at 1.4 gigahertz, these three structures are polarized. Here I'm gonna blank the polarized emission detected by Govoni and also Pizzo with the spectral index map. So overall, we have that in the central region of the cluster, we have some filamentary structure that have a spectral index, a flatter spectral index, and are also polarized at high frequency. And this is in agreement with a scenario where we are looking at relic-like emissions, so shocks that are projected onto the cluster center. If you go back and I report again the image from simulation, we can do a comparison with what we see in radio, with a caveat that this simulation was not tailored to match the case of Able 2255. And there is also another caveat that while in simulation we report the dissipated energy, in radio we see the actual radio emission. With this caveat, we can check if there are some similarities between the simulation and the observation. And I think that there are. For example, this structure here, this shock, might be associated with this region that we see outside the viral radius. We see another relic, so another shock that might be this shock in the simulation. The free straight filament in the cluster center might be associated with the shocks that are detected in the simulation here, as well as this and this relic in the outskirts.
Andrea, just 2 minutes left.
Perfect. And instead, the purple emissions of the most diffuse emission might be associated to the turbulence that is permeating the entire cluster. So overall, our observation suggests that indeed the intercluster medium is filled by shocks and turbulence up to large distances from the cluster. So just to conclude, I presented the deep LOFAR LBA and HBA images of Able 2255. these deep images allowed us to discover a faint giant envelope of emission that is embedding the entire cluster, but also a number of filamentary structure inside inside this giant emission. From a spectral index analysis, it seems that the spectral index distribution is not uniform, and we generally see that the flat spectrum emission is associated with the filamentary structure, while the more diffuse emission is associated with the steepest spectrum emission. And we interpreted this with as an evidence of a mixture of shocks and turbulence that are filling the ICM. And what I think that these results are very interesting because they are proving that with radio observation we can start to detect and prove the physics of intracluster medium in a new regimes at very large distances from the cluster center that is not accessible at any other wavelengths. So thank you for your attention, and I'm ready to take your questions.
Boy, those are beautiful images down at low frequencies, and I'm personally very pleased to see this. I long ago had a sharp argument with Herder Brown where I opined that we would never be able to make images with the LBA in the general field, and I'm so happy to see that I'm dead wrong. Kudos to those who figured this out. Any hands up, please? Well, while we're waiting for people to generate questions, I have one. I think you flashed, was that an L-band in polarization image of 2255?
Yes, that's correct.
So have you attempted to make any spectral index images between the HBA and the L-band images, or any information there?
Yeah, we have a spectral index map between Westerbork, 1.2 gigahertz observation, and HBA data, and these were published in the first paper on this cluster that we published last year. And indeed, already from that images, we were suspecting that the region of the three filaments was flatter compared to the halo. Of course, with the Westerbork image, it is very deep because we are a full synthesis observation. We were not able to map all the structure that is arising in these very deep LOFAR data sets.
Yeah, those regions of the -2 spectrum, I presume they're not visible at L-band?
No. Basically, the halo detected in L-band is reaching this region here.
And sorry, I lost my train of thought there. Oh yes, you have hundreds of more hours now assigned to do deeper imaging. Is this correct?
Yes.
And so what are the goals? What are you hoping to improve here?
Yeah, I would like to see how much extended is this diffuse radio emission, because
you mean further out to larger radii?
That's a question that I would like to address with a new data, because it might be possible that at some point this emission has edges, because it might be confined, for example, by what is called the splashback radius. And this would be very cool because it has not been observed in any other, in the X-rays or radio in any other galaxy cluster. So that's one of the things that I would like to see with the new data.
There is a hand up, Namir. Did you have a question?
Yeah. Hi, Rick. Just very briefly, I wanted to just follow on your comment. It's just amazing to see the wide field imaging with the LBA. I didn't think it was going to be possible either, and it's just amazing. It's really breaking open the field. It'll be interesting to see it. For me personally, I'd like to see it turn to some extended galactic objects eventually.
Yeah,
and
maybe if I add here to Rick and Namir, I think we're all amazed that this worked. But can you remember the arguments why it shouldn't?
The argument between me and her had everything to do with the angular scale of isoplanar regions at low frequencies. As you go down in frequency, the coherent scale gets smaller, and the amount of flux you've got also goes smaller. So Yeah, but without getting into details, that was the essence of the argument.
Yeah, for me, it was the sparse distribution of antennas in the individual stations. I thought you needed to have more antennas filling the station as opposed to the ring. But you know, you figured it out. It's amazing. Congratulations.
So did I see a hand up from Pratik? Was there a question there or not? I guess not. Okay, well, I think we are now a little bit past the time. I want to thank everybody for their close attention, the speakers for keeping on time scale and for their beautiful presentations. There is the Slack channel and the Gather Town assembly place, which I encourage people to get to. Me, it's lunchtime here, so I gotta head out to lunch. Thanks to everybody, and we'll see you at the next session.